In this problem, we're going to use Hess's law to determine the enthalpy of the following overall reaction given the steps that follow. So here's our overall reaction that we're going to find the enthalpy for. Hess's law says that if we know the steps, which we do in the following three reactions, I'll label those 1, 2, 3. So if we know those steps, we can, and they add together to get our overall reaction, then the enthalpy can be calculated for the overall reaction. So I'm going to start just by looking at the overall reaction. I see CO2 on the left. So I want that on the left. And there's only one reaction that has CO2 on the left, and it's equation number 3. But you notice there's 2 CO2. We got to get rid of the 2 and just get 1. So we're going to see how to do that. So we're going to go ahead and write it out. I'm going to ignore the states for right now. And the overall enthalpy is 3511.1 kilojoules. And now I want only 1 CO2, not 2. So I'm going to divide everything, the entire equation, I'm going to divide by 2. Now you look at that 7/2 O2. This is going to get a little strange, but half of that would be 7/4. And I'm going to divide my enthalpy by half. So what that allows now is for 1 CO2 like I have in that top equation. So then I'm just going left to right here. We don't have to put these equations in any particular order. So looking here at the next is a product. That's carbon. It's on the right. And you can see that only equation 2 has carbon and it's on the right. But there's 2 of them. So again, we're going to have to divide by 2 when we get there. I'm going to line up my arrows so this doesn't get too disorganized. And my enthalpy equals 190.6 kilojoules. Okay. So I only want 1 carbon, and again, this is the only equation with carbon, so I don't have to worry about any algebraic canceling or anything. But I'm gonna divide everything by 2 so that I can get that 1 carbon, and then the 190.6 will also be divided by 2. Okay, now the last one's going to be tricky because we need to bring in equation 1. And this one's kind of tough. So you'll notice in this overall reaction that we've got 1 molecule of O2. And the only place we see O2 in what we've done so far is right here. We've got O2. And so there's 7/4 of an O2 molecule. So that's a problem. We only want 1 molecule of water. So we're going to need to algebraically cancel some of that oxygen, and the way we're going to do it is we need oxygen on the left. We're going to need to have oxygen on the left. So this equation right here, we're going to flip. So I'm going to take the H2 plus O2. I'm going to flip the whole thing. And I'm going to put the H2O on the right, and then I'm going to balance it as we have there. So now I need to look what will algebraically cancel. So you can see there's water here in that equation, and then the top one there's water. And there's no water in the overall equation. So I need to multiply these equations by something in such a way that those water molecules cancel. So if I multiply this bottom equation by 3/2, those water molecules will cancel. You'll also notice that there is 3/2 of a hydrogen mole of hydrogen, not molecule, 3/2 of a mole of hydrogen in that second equation. So this is going to work if I multiply everything by 3/2. Now, if you notice with oxygen, we've got 1/2 of a mole of oxygen. I need to multiply that also by 3/2. So 3/2 times 1/2 is 3/4. So I multiplied the 3/2 by 1/2 and I got 3/4. So now we're ready to add, except we need to take this first equation here, delta H, it is flipped. We flipped it, so it's going to be minus 643 kilojoules, and we multiplied that by 3/2. So let's algebraically add this whole thing together. So first of all, carbon dioxide does not cancel with anything, and we're going to, instead of writing it as 2/2, we're going to write it as CO2. So that gets rid of carbon dioxide, or takes care of it, doesn't get rid of it. Then we have water. We'll notice that the water cancels. I've got 3/2 water on both sides of the equation. So that's good. And then you'll notice that the C2H6 is not in the overall equation, and it's a half here on the right and half a mole there on the left, so that cancels. If we look in the second equation here, we see 2/2 of carbon. 2/2 of carbon is 1, so that we're going to put the carbon down. That takes care of carbon. Then we'll notice with hydrogen, and I'm saving oxygen to the end because it's tricky. The hydrogen, we don't want it. It's not in the overall reaction. We have 3/2 and 3/2. It cancels. And now we're going to deal with oxygen. So 7/4 minus 3/4 equals 4/4. So that's going to be 1. So we're going to get rid of the oxygen on the left, which we don't want. We're going to subtract 7 minus 3. That gives us 4/4, which is 1 oxygen molecule. And we've got what we wanted now from our, as you can see from our overall equation. I'm going to put the states in. Carbon's a solid, oxygen is a gas. And now I'm going to algebraically add the enthalpies and divide and as it shows. You can see that I have gone ahead and multiplied by half, and then also here multiplied by 3/2 to get my enthalpies for the way we've set up the reaction. So it's going to be 1755.6 kilojoules plus 95.3 kilojoules, and then 965 kilojoules. You'll notice that the first common decimal place is the ones place, so when we add those all up, this is negative minus 965. We get a total of 886 kilojoules. So delta H equals, it's positive, 886 kilojoules. So we've used Hess's law to rearrange equations that were steps to our overall equations and calculate the enthalpy of the overall reaction.